Okay, in today's lecture, we're going to talk more about chemical equilibrium and the equilibrium constant. So this is from the last lecture where we introduced the concept of chemical equilibrium. If you didn't catch that one, feel free to go back and watch it. But in general, it's always products over reactants with the products raised to their respective stoichiometric coefficients, right? Products over reactants. You can do this with concentrations, as I've indicated here with the brackets, but you can also do this with pressures. Doesn't really matter. But these two things are going to be related, and you can actually derive the relationship of these two equilibrium constants, depending on if you're talking about pressures or concentrations. So remember, for the ideal gas law, PV equals nRT, or P equals nRT over V. Well, this N over V right here is essentially a concentration, moles per liter. And so what we have here is a way to relate pressure and concentration. Okay, so if we think about Kp, for some reaction here, let's think A is maybe combining with B amounts of B to form in a reversible equilibrium reaction, C amounts of C. So I'm writing just a generalized expression, right? A combining with B to make C, and there's A moles of A, B moles of B, and C moles of C. So if I wanted to write Kp here, I would write products over reactants, so it's the pressure of C raised to the power of C over the reactants, pressure of A raised to the power of A, times the pressure of B raised to the power of B. Now, I can replace each of these pressures, whether it's A, B, or C, with moles of C, right, over the volume, along with R and T. So this Kp actually becomes, and let me move this over a little bit, this pressure becomes a concentration, right? This is a concentration times RT. So this is going to be the concentration of C RT raised to the power of C. Right? All I've done here is replace pressure of C with concentration RT of C. And the bottom then looks similar, concentration of A, RT to the A, concentration of B, RT to the B. And right on brand, I'm running out of room on the edge of the screen. If only I had used any of this blank space right here. Oh well, next time. So now that we have this written for concentration, I could factor out all of these RTs, right? I can factor out these RTs to say, well, I have RT to the C over RT to the B, to the A, times RT to the B, and multiply that by my C to the C over A to the A over B to the B. So I'm just taking this big expression over here and sort of separating it out into two multiplicative terms, right? This right here is Kc. That's my equilibrium expression when I'm using concentrations. So if all this is Kp, all of this is Kp, then it's no surprise that Kp is equal to Kc, all of this, right, times RT raised to the delta N, where delta N is moles of product minus moles of reactants, okay? So what I'm doing here is combining everything here in the red box, because they're all the same RT, I can combine all of that to be RT to the power of C minus A minus B, right? Which is the change in moles of gas from products to reactants, right? Moles of gaseous product, C, minus moles of gaseous reactant, A plus B, gives me C minus A minus B. That's exactly what I've written here. Okay, and so therefore we've derived this relationship Kp equals Kc RT to the delta N. Okay. A lot of times in chemistry, students are just like memorizing or told these formulas, and there's no real appreciation for where they come from or how they're related, right? In this case, they're related, assuming we can describe these gases with the ideal gas law. So if that's not the case, this would not hold true. But for most of the things we teach in general chemistry, that's a safe assumption to make, and one we will make here. So let's put this into action and try to actually calculate Kp for this reaction and the conditions shown here. Feel free to pause the video here and try it yourself. Otherwise, I'll continue and solve it. So reading something like this, we have to calculate Kp from Kc. I automatically, realize that, well, I'm going to need this Kp is Kc RT to the delta N. And importantly, this delta N here is only moles of gas. So if it's solid, liquid, or aqueous, don't count it in your change in moles. So let's go through and plug everything in. Kc is 9.60. Okay, the R that makes sense to use here is 0.08206, right? The same R we use in PV equals nRT, given moles and liter, which is concentrations and what we care about. So using this value of R makes sense because it's the one with the units of liters, atmospheres, per mole Kelvin, right? And we want the moles per liter because we're using Kc and concentrations, okay? We're going to be left with atmospheres because, I should leave some space here for the temperature, because we're talking about Kp, which should be using atmospheres, for example. So now I need the temperature. The temperature, though, should be in Kelvin, right? This suggests Kelvin right here. So I'm going to take this 300 and I'm going to add 273 to it. You can add 273.15 if you want to be a little bit more specific and get 573.15. And now we have delta N, so we've plugged in R. We've plugged in T with the correct units. We have to plug in delta N, so let's count up. Everything's a gas here, so it's not going to, there's not anything we have to ignore that's a solid, liquid, or aqueous. And so we just take moles of product, so 2, and we subtract moles of the reactants, 3 and 1, so that's 4. 2 minus 4, our delta N here is -2. And so all of this, in parentheses, gets raised to -2. And so now you mash a bunch of buttons on your calculator, and you get a Kp value of 0.00434. And remember what we talked about in last lecture, that these values of equilibrium constants, whether it's Kp or whether it's Kc, they have no units, right? These are unitless quantities, dimensionless quantities. So this will not have pressure units at the end. The reason is because these pressures that you would put in right here are technically relative to a 1 atmospheric pressure. And the concentrations you would put in here are technically relative to a another standard concentration. And so we're really using activities, but that's a bit beyond the scope of this course. Just know in the end here, these are dimensionless quantities at the end. So that's how you would solve a problem with calculating between Kp and Kc. Now, a little bit more about equilibrium. Okay, we've talked a lot in the previous lecture about a reaction of N2O4 in the gas phase, dissociating the nitrogen-nitrogen bond breaking to make NO2 gas plus NO2 gas. So you can imagine filling a container with just N2O4 and letting it proceed to the right. That's what's shown here in experiment 4, right? Initially, there's N2O4. There's no NO2 initially. I set up that experiment. I let it go. I come back a day later once equilibrium is established. Here are the concentrations I'm left with. Okay, my Kc is going to be products over reactants, so NO2 squared over N2O4. What if instead I start the reaction with just products written here, just NO2? So instead in my test tube of putting N2O4, I just load in a bunch of NO2. Well, that's experiment 3 here. I'm just loading in NO2 and no N2O4. And I let the reaction happen. It goes back to the left, making N2O4. I come back a day later. Where does it end up? It ends up in basically the same place as it did for experiment 4. The ratio of products to reactants at equilibrium gives me the same value. So the point here is it doesn't matter which of these experiments I start with, the ending place is the same, and the ending place is always described by these equilibrium constants. And so that's what's shown here in a graph for NO2, whether it's experiment 4 when you're starting with no NO2, or experiment 3 when you're starting with a bunch of NO2, at these long time frames, right? Out here, there be equilibrium. Okay, at long time frames, the reaction is going to settle out where it wants to settle out naturally, wherever this equilibrium is. So the final ratio of these two compounds remains constant, assuming that these are all done at a certain temperature, not mattering what initial concentrations I start with. Now, the exact size of this equilibrium constant tells you a little bit something about where the reaction is going to end up. So, these Kc values less than 1 here tells you that this ratio of products to reactants, once equilibrium is achieved, there's going to be less product than reactants, so that the ratio, the denominator, is bigger, and I get a value less than 1. Right? So if K is much, much greater than 1, then the reaction favors products, and the reaction really goes heavily, you could just draw a single arrow to approximate it, heavily to products. We say the equilibrium lies to the right, or equilibrium is to the right, or products are favored. If K is, well, should be like this. If K is much, much less than 1, right, like right in here, then the reaction is favoring reactants. And so although overall, this is, we're thinking of this as a reversible reaction, right? In actuality, if K for this reaction is much less than 1, then the reaction favors reactants. We say equilibrium lies to the left, that reactants dominate at equilibrium. And if a K value is very, very small, that makes sense. That denominator in the ratio is outweighing the numerator. The reactants are outweighing the products. Now, the equilibrium constant of a reaction, if I write the reaction products to reactants, so if I flip instead of A to B, right, if I write B to A, that matters, okay? And it doesn't look like it should matter since we're using these arrows indicating that all these things are reversible, but it does. This is part of sort of, the standard practice, right, and the convention, I should say, of chemical equilibrium. Is dependent on what these Kc values are, is dependent on how I set up and write the reaction. Okay, so look at this reaction that we've been talking about. N2O4 goes to 2 NO2s. Here, technically, NO2s are the product. N2O4 is the reactant, right? Reactants going to products. That's how we're thinking of it. But we realize that this is a dynamic process. All the time, products can be turning back into reactants while reactants are turning into products, right? But since we've written it this way, that dictates that it's products over reactants and gives us a Kc value like this. If I write it and flip this arrow, if I flip these two things, and instead write 2 NO2, reversibly goes to N2O4, then I flip numerator and denominator. Okay? So, Kc of 1, if I'm labeling these, 1 and 2, is the reciprocal of Kc2. Okay? Basically, too long, don't read, TLDR. If a reaction flips, take reciprocal. Spelling will not be graded. Take the reciprocal of the equilibrium constant. All right, so it's very dependent on how we write this reaction. It also depends on the stoichiometries, right? Instead of writing 1 N2O4 to 2 NO2s, we could write 2 N2O4s to 4 NO2s, but that would affect these superscripts, right? And should affect Kc. And it does. So look at this. Here's our prototypical reaction. Reaction 1. If we multiply the reaction through by 2, well, now instead of being NO2 squared over N2O4 to the first, it's NO2 to the fourth over N2O4 to the second. Right? I've essentially squared the top and the bottom of this. And so I square Kc. Right? So here the TLDR is if reaction is multiplied through, or say multiplied by a number, raise the equilibrium constant to power of that number. Power of hashtag, right? So here we took reaction 1, we multiplied it by 2, so we're going to take Kc of 1 and raise it to the second power to get my new Kc of reaction 2. The same will be true if you're dividing. Just think about multiplying by a fraction, right? If I'm going from 2 to 1, I'm multiplying by 1/2, so I better raise the Kc of this to the 1/2 power. Now, there's one other way we can manipulate our reactions here, and that is adding a bunch up. Remember back to thermodynamics and thermochemistry, Hess's law, a lot of times we might add up different reactions to tell us something about an overall reaction, okay? Because maybe reactions 1 and 2 are well known and characterized, and we know the K values, the equilibrium constants, and I want to say, well, this, imaginary reaction 3 that I'm interested in, what will the equilibrium of that be? And the beauty is I don't have to actually run that reaction, look up in a table of data to see if it's been cataloged. All I do is take reactions 1 and 2 and combine them in a clever way, right? The TLDR here is if reactions are added together, then we multiply the equilibrium constants together. Right? So in this Figment reaction, 2 NOBr plus Cl2 goes to 2 NOs plus 2 BrCl. Maybe I can look up these two separate reactions 1 and 2. I see if I add these reactions together, bromine cancels out, right? And I'm left with 2 NOBr plus Cl2 goes to 2 NO plus 2 BrCl, which is exactly what I want here in this third reaction. So I can add these two reactions, which have known equilibrium constants, K1 and K2. So I simply multiplied together K1 times K2, 0.014 times 7.2, to get 0.10. Again, they're all dimensionless here, these equilibrium constants, so the answer here would just be 0.1. The equilibrium constant of this new reaction is the product of the two equilibrium constants for the reactions I added together. All right, so this is usually really useful in calculating more complex reactions, equilibrium constants, from simple steps. So here we have a practice problem where we're putting all of this together, the concept of the equilibrium constant, manipulating reactions to figure out what is the value of Kc for this overall reaction here. Can't look it up in a table. Well, maybe you can, but assume we can't look it up in a table. But we can look up in a table these reactions 1 and 2. that have corresponding equilibrium constants here and here. How can you calculate the reaction equilibrium constant given these bits of information? Feel free to pause the video here and solve it. Otherwise, I'm going to go forth and solve it. Okay, so the strategy here is to figure out how exactly do I have to, manipulate these reactions 1 and 2 to yield overall this reaction that I want. And so hopefully you can see just looking at HF, well, here's HF, and there's 2 of them. Here's F minus, and there's 2 of them. I probably have to multiply reaction 1, multiply it by 2. So if I'm taking reaction 1 and multiplying it by 2, this means, right, what happens when we multiply a reaction? If the reaction is multiplied by a number here, 2, then raise the constant to that power. So I'm going to raise the equilibrium constant of reaction 1 to the second power. I square it. So I take 6.8 times 10 to the negative 4, and I square it. Now, what am I going to do with this reaction? 2HF, 2H plus, 2F minus, now that I've multiplied it through by 2, and now that I've squared its equilibrium constant? Well, I have to combine it with reaction 2, but reaction 2 looks like it's backwards. H2C2O4 is on the left when clearly I need it on the right. And so I have to take and flip reaction 2. If a reaction flips, take the reciprocal of the equilibrium constant. So I need to flip this, and I need to take Kc for reaction 2 and do 1 over that. All right, so I'm going to take the reciprocal, which is this to the negative first power, or 1 over that number, to flip this reaction, to move the reactants to products and the products to reactants. And now that I do that, you should be able to see that you would have 2HF goes to 2H plus 2F minus. And you would have 2H plus C2O4 2 minus goes to H2 C2O4. And now I can add these 2 steps up, and the H pluses will drop out, and I'll have overall the exact reaction I want, 2HF plus C2O4 2 minus goes to 2F minus plus H2 C2O4. Right? That's the reaction I want. Now, when I add up these 2 reactions, which have these new equilibrium constants we're calculating, what happens when I add reactions? If I add reactions together, I multiply the constants together. So overall, my Kc for this overall reaction is going to be these multiplied by each other. It's going to be 6.8 times 10 to the negative 4 squared times 1 over 3.8 times 10 to the negative 6. (6.8 times 10 to the negative 4 squared divided by 3.8 times 10 to the negative 6 gives me a Kc value in the end of 0.12. That is my final answer here. And conceptually, I can look at this and now realize that, well, this Kc value is less than 1. That means at equilibrium, this reaction that I'm sort of imagining taking place here, right, is going to lie mostly with products, right? Or sorry, mostly with reactants. Reactants are going to maybe not dominate, but be more prevalent than the products as this reaction is written, because my Kc value is less than 1. So the denominator, meaning the reactants, is larger than the numerator, the products. The final thing I want to get to here is just briefly some things we have to watch out for when we're writing equilibrium constants and when we're thinking about what to include as far as solid, liquids, gases, aqueous. First, some vocabulary. Homogeneous equilibrium occurs when all the reactants and products are in the same phase. So everything we've done thus far has been homogeneous or homogeneous equilibrium, right? So this is the same here. Everything is gases, right? So this is homogeneous because everything is aqueous, right? This is homogeneous because everything is a gas. Heterogeneous equilibria, right, happens when something in the equilibrium is in a different phase, okay? And so what we'll see is that, well, you can have a solid decompose to give maybe another solid and a gas. And so this would be, there could be a double arrow here because it's an equilibrium. This would be heterogeneous equilibrium because we have solids here and we have a gas. And when we're talking about heterogeneous equilibria, right, be extra careful that you're paying attention to the phases. And note the following. The value used for concentration of a pure solid or liquid is always 1. So if I was writing Kc here, Kc would be products over reactants, but it's just the concentration of C, because the concentration of B is a solid, it's 1. The concentration of A, it's a solid, it's 1. And you'd say, well, how can that make sense? How can the concentration of a solid or liquid always be 1? And the trick here is that, again, these K values are dimensionless, and that's because really these concentrations aren't pure concentrations, right? But they're referenced to some standard concentration, right? And we're worried more about how those concentrations change. So you can think about a gas. If you put gas in a container, right? And there's maybe 5 gas particles here, right? That occupy this certain volume, okay? If I remove some of the gas, okay? If I remove some of this gas, now there's 4. The gas is going to expand to fill the container, right? So the number of things per volume, that does change when I remove some of the gas because the rest of the gases expand. They're getting more dilute. The concentration is decreasing. But instead of that gas model, think of a solid, okay? Here's a solid. Let's break it into 4 quadrants here. And let me remove this quadrant. I have moved some amount of moles of stuff, but I've also correspondingly removed the volume. So the density or the concentration here remains the same for the volume. So solids and liquids, whenever you remove some of the moles of the stuff, you remove exactly the corresponding volume for that thing, right? Gases are not that way because the remaining gases expand to fill the rest of the volume, so their density changes, right? Solids and liquids are not the case. Okay, solids and liquids will always be 1. Okay, so the TLDR here only consider gases and aqueous in our equilibrium expressions, Kc or Kp. Because aqueous is the same way. It's an ion that is existing in water. And so you remove just that ion, you leave the volume of water. And so the amount, the density of that ion does change, kind of like a gas. The rest of the ions sort of fill the rest of the water space. So gases and aqueous, we are going to concern ourselves with those. We are not going to concern ourselves, okay, with liquids or solids. So any solid or liquid doesn't affect Kc or Kp. So here's a more practical example. You can set up in a jar, and this is actually pretty fun to see, a little pile of calcium carbonate, right? And you can start your reaction, okay? And you can come back later, and you can see that some of this calcium carbonate has gone away, and you've generated a little bit of calcium oxide and some carbon dioxide gas. The equilibrium constant for this reaction, I ignore solids, I ignored solids, so Kc is just the concentration of CO2 in the gas phase. Okay, written in terms of Kp, it's just the pressure of CO2 in the gas phase. Equilibrium here, again, that is where the reaction ends up, doesn't depend at all on how much calcium carbonate you start with. Which is a bit crazy, right? It doesn't matter if I start it with 100 grams of calcium carbonate, okay, or 1,000 grams of calcium carbonate. The pressure of the CO2 at the end of the reaction, the concentration of CO2 at the end of the reaction is going to be the same, which is crazy to think about, but that's how equilibrium works. It doesn't really depend on the solids or liquids, just on the gases or aqueous. As we move forward, we'll see similar things with equilibria that look maybe more in the aqueous phase. So you could think about lead chloride, which solubility rules tell us that is a solid in water. Or when we put that in water, I should say, this solid in water, we get some Pb2+. And chlorine minus. And the equilibrium expression here would just be concentration of Pb, 2+, concentration of CO minus squared. There is no denominator. This is a solid. Don't include it. The equilibrium expression only depends here on the products Pb, 2+ and Cl minus squared. Okay, so in this lecture, we've talked a lot about heterogeneous and homogeneous equilibrium, but more about equilibrium constants as a whole and how they really are changed or manipulated as we multiply reactions by certain numbers, as we flip reactions, as we add different reactions together, and talked about this notion of equilibrium, which is a little funny that it doesn't really matter where you start. Chemical equilibrium is always about where you finish, and that Kc value is a certain value for that certain reaction at that temperature. And if I run the reaction again at the same temperature, I'm always going to wind up eventually in the same spot with the same equilibrium constant, right? It's useful in a practical sense because these reactions that you might not have spelled out for you in the literature and might not be known, you can actually predict ahead of time, where is equilibrium going to be? Is this a beneficial process to start with these reactants if I'm not going to make very much products? What is the equilibrium constant for this? I add up these reactions, which I know the equilibrium constants for, and now I can make a prediction based on, is this reaction really worth doing, maybe in an economic sense in industrial chemistry? So next time we'll move into much more quantitatively figuring out just not is this reaction worthwhile, but exactly how much product will I make? And that gets a little bit more mathematical, using things like the quadratic formula to figure out exactly how much product I make given some starting conditions and an equilibrium constant. But that'll do it for this lecture. See you next time.